In this video, we want to find the asymptotes, all of them, for each of the given rational functions. There's 3 of them. This is the main one here. You can pause the video and see if you can work these out. Again, we're looking for any vertical asymptotes, any horizontal asymptotes, and there could be oblique or slanted asymptotes, especially on this first one here. So let me just go through them, and you can pause wherever you want. Try to work these out. Not asking you to graph on this one, just finding the asymptotes. That was number 2, and then this is number 3. Okay, I'm going to start with number 3. This is the easier one of the 3. So I'll start with this one, and then just give you the general information that you need. So we're looking at rational functions. A rational function can have one or more vertical asymptotes. It can have a horizontal asymptote or a slant or oblique, but it only have one. It can't have both a horizontal and a slant. It'll just have one or the other. So here's the general procedure. Let's look at the vertical first. The vertical asymptotes, those are, again, these are lines in general that the graph approaches. In general, it doesn't touch. It is possible for the graph to cross or touch a horizontal asymptote or a slanted or oblique asymptote, but it's never going to cross a vertical, because the way you find the vertical asymptotes is where the denominator is 0. So all you have to look at is make sure first of all that the function is reduced to lowest terms. 3x over x plus 4, that's about, there's no common factors, so check for common factors. Then for the vertical, you look at numbers and make the denominator 0. Well, x plus 4 is equal to 0 when x is equal to negative 4. So right away we know that x equal negative 4 is a vertical asymptote. The graph is going to approach these either from the right or the left or both. And usually we draw we do the actual graph, we draw the asymptotes as broken or dotted lines. Now for the horizontal vertical asymptotes, and let me draw these. So the vertical asymptote, we got a horizontal asymptote, or we can have a slanted or oblique. So here's the way it works. If the degree of the numerator is less than or equal to the degree of the denominator, then you're going to have a horizontal. Now if the degree of the numerator is less than the degree of the denominator, y equals 0, or the x-axis will always be a horizontal asymptote. So if I had made this a 3 instead of a 3x, then the degree of the numerator would be 0, and 0 is less than the degree of the denominator, which is 1. So y equals 0. If I don't have the x there, y equals 0 would be the horizontal asymptote. In this case, the degrees are the same. So notice what happens if I divide the numerator and the denominator by x. The numerator becomes 3, x divided by x is 1, and 4 divided by x is 4 over x. So what happens to the graph, again, if you have an asymptote? The graph approaches the asymptote, whether it's a horizontal or slant, as x goes to infinity, minus infinity, or plus infinity. So what happens to this as x gets real large? Say x is 10, 1,000, 1,000,000. Basically, this goes to 0. So what's left? 3 over 1. So whenever the degree of the numerator and the denominator is the same, like here, this is a 1 and this is a 1, it's always this coefficient on the x on top over the coefficient on the bottom, so it's 3 over 1. So it's going to be y equal to 3. So for number 3, the vertical asymptote is x equal to negative 4, and the horizontal is y equal to 3. The graph will approach those vertical and horizontal lines. Let's go to the next one. Again, you can pause. If you haven't done it, you can pause the video here. Try to look at this. So for this one, the degree of the numerator is 3. The degree of the denominator is 4. So in this case, 3 is less than 4. So basically what happens here is the denominator gets real large as x goes to infinity or minus infinity. So technically this goes to 0. So the horizontal asymptote is y equal to 0. Now again, for the vertical asymptotes, those come from numbers that make the denominator 0 but not the numerator. So let's look at the denominator can be factored out. The difference is squares, so it's x squared minus 1 and x squared plus 1. Now x squared plus 1 is never 0 for real numbers. Now x squared minus 1 can be factored into x minus 1 and x plus 1. You can see in the factored form, the numbers that make that denominator 0 are going to be x equal to 1 for this factor here. 1 minus 1 will be 0. And for the next factor, x plus 1 will be 0 and minus 1. So the vertical asymptotes are going to be x equal to 1 and x equal to negative 1. Again, 1 and negative 1 is where the function is not defined. So there's going to be a break in the graph there. Unlike polynomial graphs, they're nice and smooth because they're defined for all real numbers. Rational functions have a lot of times will have breaks in the graph, and that of course is what occurs where you have the vertical asymptotes, because those are the points where or the values where the function is not defined. Now again, repeat that the vertical asymptotes will come from numbers that make the denominator 0, but not the numerator. Okay, now I'll show you an example of that a little bit later on. For now, the answers here are y equals 0 is the horizontal asymptote, and x equal 1, x equal negative 1 are the vertical asymptote. Now if I had made this an x to the 4th here, x to the 4th, then the degree of the numerator and denominator would be the same. So I would take this coefficient of the x to the 4th on top over the 1 on the bottom, and then the horizontal asymptote would be y equal to 1 in that case. But if the degree of the numerator is less than the degree of the denominator, the horizontal will always be y equal to 0. So those are the answers to this one. Now let's go to the main one here. Now if the degree of the numerator is larger than the degree of the denominator, then there is no horizontal. But if the degree is 1 more than the degree of the denominator, then you have a slant asymptote. So first let's find the vertical. Those are the easiest ones to find. So let's factor out an x from the denominator. Now x squared plus 1, or x squared plus 3 I should say, because of the plus sign there, there's no value that makes that factor 0. So the only value that makes the denominator 0 is x equal to 0. So I can easily say the vertical asymptote is x equals 0. The only restriction is, again, and you can check that as you go through there, make sure that that number doesn't make the numerator 0. Well, if I put a 0 where the x is in the numerator, put a 0 right there, 0 to the 4th is 0 times 3 is 0, and 4, yeah, I get 4. So this is okay. I'll show you an example of what I'm talking about a little bit later on. So this one, like we said, doesn't have a horizontal asymptote, but it does have an oblique. So how do we get the oblique asymptote? We simply take the expression in the numerator, 3x to the 4th plus 4, and divide this odd-long division. Now the denominator were a first-degree binomial, we could use synthetic division, but in this case it's x to the 3rd then is a divisor. So we divide x to the 3rd into 3x to the 4th, and that gives me 3x. And then again, just like dividing regular polynomials by, in this case, a binomial, 3x times x to the 3rd is 3x to the 4th. And then 3x times 3x is a plus 9 x squared. And you continue dividing until the degree of the remainder is less than the degree of the divisor. The divisor has degree 3, so here we just subtract at this point. 3x to the 4th, subtract 3x to the 4th. This is 0. And then here, it's 0 subtract the 9x to the 2nd. So this gives me a minus 9 x squared. And then 0 subtracted from 4 is just 4, so bring that down. Now notice this minus 9 x squared plus 4 is actually the remainder. It has degree 2. The divisor has degree 3, so we can stop division right there. That's the remainder. So basically then I can say that this is, if I were to give the answer to this, I would say that the answer to the quotient is 3x, and then I put a plus here, and then I take the remainder, which is minus 9 x squared plus 4, and divided by the divisor, 3x to the 3rd plus 3x. Now we're looking at the behavior. What happens to the graph is x gets real large or x gets real small. X goes to infinity or x goes to minus infinity. So what happens here is x gets real large, this denominator gets real large. So basically you're dividing a number by a much larger number here, because this is the power in this one is x to the third, this one is x squared. So basically this goes to 0. As x goes to infinity, minus infinity or plus infinity, this goes to 0. Well, what does that leave us with? 3x. So here I can say the oblique, well, I'll just put SA, oblique or slant asymptote. And here all you do is you take y and set it equal to whatever the quotient was, 3x. So we were to graph this rational function. The graph in a certain interval will approach the line y equal to 3x. So here's the procedure for finding the oblique or slant asymptote. If the degree of the numerator is 1 more than the degree of the denominator, then it has an oblique asymptote. The way you find it is you do the synthetic division, take the numerator divided by the denominator, disregard or discard the remainder, and take your quotient and set it equal to y. And that's how you get the equation of the slant or oblique asymptote. Now, this is what I was talking about. If you got some function, I'll just call it y, equal to, say, x squared minus 4, that's divided by x minus 2. You can see that the degree of the numerator is 2, the degree of the denominator is 1, because this is x to the first. So we would say, okay, we have an oblique or slant asymptote, and the vertical asymptote would be x equal to 2. But remember, vertical asymptotes come from numbers that make the denominator 0, but not the numerator. So you can say, okay, vertical asymptote equal to x equal to 2, but 2 makes the numerator 0. 2 squared is 4, minus 4 is 0. So this is not right. There's no vertical asymptote. So what happens here? I go ahead and factor this out, and this factors into x minus 2 and x plus 2. So this is really not what we expect. In other words, it's not really a true rational function, because the x minus 2 cancels out with this one, and it basically leaves me x plus 2. But there's a condition here, because we divided x minus 2 and x minus 2, and x minus 2 is 0 when x is equal to 2. So this is only true if x does not equal to 2. So if you were to graph this function here, it's a line. So let's go ahead and graph it. If we were to graph it, let's say, okay, let x be 0 when x is 0. The y value is 2. And when x is 2, remember x cannot be 2, but let's say that if x is 2, then y is equal to 4. So okay, let's go ahead and plot those points and say, okay, we go over here, 0, 2, and 2 over, and 4 up, so we go up to this point right here. So that would be the point 24. So right there, that would be the point 24. But the graph is not defined at x equal to 2. So basically what you do is you draw the line, but you delete the point 24, because the graph or the function is not defined at that point. Okay, thanks for watching. We'll see you next time.